Quasi-hereditary algebras, lecture 3, highest weight categories. Let us recall the notion of the standard module, which we defined on the previous lecture. Let K be an algebraically closed field, and A a finite-dimensional K algebra. Let L1, L2, and so on Lm be a full and irredundant list of representatives of isomorphism classes of simple A modules. Note that in this way, we have fixed a linear order on the set of representatives of isomorphism classes of simple A modules. And now we write them in the linear order L1, L2, and so on Lm. Let P1, P2, and so on Pm be the corresponding indecomposable projectives. So the module Pi has simple top Li, and Pi is projective. Now we can recall the definition of the standard module. So the standard module delta I, for I between 1 and m, is associated to the pair consisting of our algebra A and our fixed order on the set of representatives of isomorphism classes of simple A modules. And the module delta I is defined as the quotient of Pi, modulo the trace in Pi of projectives Pi plus 1, Pi plus 2, and so on up to Pm. In other words, we take Pi and we take in it the submodule generated by all simple subquotients Lj, where j is strictly greater than I, and we factor out this submodule. The outcome is our standard module delta I. Now we can define the notion of a highest weight category. Definition: we say that the category of finite-dimensional A modules, together with our fixed order on the set of representatives of simple A modules, is a highest weight category, provided that the following two conditions are satisfied. First of all, for any I between 1 and m, the kernel of the projection from delta I to Li has a filtration whose subquotients are Lj, where j is strictly smaller than I. And the second condition is that for each I from 1 to m, the kernel of the projection from Pi to delta I has a filtration whose subquotients are delta j's, where j is strictly greater than I. It's very important to point out that in both cases, the inequalities, in the first case, j is strictly smaller than I, and in the second case, j is strictly bigger than I. It's important that these inequalities are strict. And note that from the first condition, we in particular get that the multiplicity of Li in delta I is 1. So if the first condition is satisfied, then the multiplicity of Li in delta I is 1 for each I. And in particular, if these conditions are satisfied, we get that the matrix of composition multiplicities in standard modules, this matrix is lower triangular with ones on the main diagonal. And this definition goes back to the original paper by Klein, Parshall, and Scott, which is called Finite-Dimensional Algebras and Highest Weight Categories, and which appeared in Kred's journal in 1988. Here is an example. Consider the path algebra of the following quiver. We have 4 vertices, 1, 2, 3, and 4, and 3 arrows, from 1 to 3, from 3 to 2, and from 3 to 4. So here are the diagrams of projective modules, and here we denote by I the simple subquotient Li. So the projective at 1 starts at 1. Recall that the projective module consists of all paths which start at a certain vertex. So P1 starts at 1, and then we go by arrow to 3, so the next submodule is 3, and from 3 we can go to both 2 and 4. So after 3 we have 2 and 4. So that's the diagram of P1. The vertex 2 is a sink, so P2 is equal to L2. P3 we start from 3, and then by arrows we go to 2 and to 4, and P4 is just 4. Now, when we have all projectives, we can write down the standard modules. we start from the maximal 4. So by definition, delta 4 is just P4, which in our case is a simple module L4. To produce delta 3, we take P3 and we factor out the submodule generated by all 4s. Here is the submodule, we factor it out, and we get a module which has top 3 and socle 2. P2 is simple, so delta 2 is L2, just directly by definition. And now delta 1. So P1 is this projective, and now we have to factor out the submodule which is generated by all simples 2, 3, and 4. So if you take 2, 4, and 3, everything what is generated by them should be factored out. So we factor out this part, and we get the simple L1. So delta 1 is L1, delta 2 is L2, delta 4 is L4, while delta 3 is a module of length 2. It has 3 on top and 2 in the socle. Now we can check our conditions. So here are the filtrations for standard modules. Of course, when the standard module is simple, then the kernel of the surjection from the standard on the simple is trivial, so there is nothing to check. The only non-trivial case is delta 3. Delta 3 surjects onto 3, and the kernel is just L2. The index 2 is strictly smaller than 3, so everything is fine. And finally, let us check the filtrations of projectives. So P4 is just delta 4, we know that. For P4, everything is great. P3, it's a module 3 on top and 2 and 4 in the socle. So 4 is just our delta 4, and then 3, 2 is our delta 3. So P3 has a filtration whose subquotients are deltas. P2 is simple, it coincides with its delta, there is nothing to check. And finally P1. So P1 has 1 on top, and then we have P3 as a submodule, which in turn has delta 3 here and delta 4 as a submodule. So P1 has a filtration of length 3. It starts with delta 4, then it covers the P3 submodule, we add up delta 3, and finally we add delta 1. So P1 also has a filtration with standard subquotients, and so the category of modules over the path algebra of the skewer is indeed a highest weight category. Now, as a first property of highest weight categories, let us discuss global dimension for highest weight categories. Recall that the global dimension of the category A mod is the supremum of the projective dimensions of all objects in this category. Since any object in this category has a composition series, this coincides with the maximum of the projective dimensions of simple A modules. So the first homological property for highest weight categories is the following theorem. Assume that A mod with respect to some linear order less than or equal to is a highest weight category. Then the global dimension of this A mod is at most 2m minus 2. So here m, as before, the number of simple A modules. In particular, the global dimension of A mod is finite. The proof consists of two parts. In the first part, let us show by induction that the projective dimension of the module delta I is at most m minus I, for all I from 1 to m. So this is an induction which goes down. We start with I is equal to m. In this case, delta m is projective, and then its projective dimension is 0. So m minus m is 0, so this inequality is satisfied. Now let us do the induction step. Consider a short exact sequence, the kernel of the surjection from pi to delta I embedded into pi, and then this surjects onto delta I. That's a short exact sequence. And note that since A mod is a highest weight category, the kernel has a filtration whose subquotients are delta j's, with j strictly greater than I. That's our second condition in the definition. But then this means that by the inductive assumption, the projective dimension of this kernel is at most m minus I minus 1. So all delta j's, where j is strictly greater than I, have projective dimension at most m minus I minus 1. And from the dimension shift, since the projective dimension of this projective is 0, the projective dimension of delta I is at most the projective dimension of the kernel plus 1. So the projective dimension of delta I is at most m minus I. And this completes the first part of the proof. For the second part of the proof, let us show by induction that the projective dimension of Li is at most m minus 1 plus I minus 1. And if we can show this for all I, then of course to obtain the statement of the theorem, we should plug in the maximal I, which is m, and we get 2m minus 2, which is exactly the claim. So we just need to prove by induction this result. Now the induction goes from 1 and up. The basis of the induction is I is equal to 1, and that's clear because delta 1 is equal to L1. Induction step. Again, we consider the short exact sequence. The kernel of the surjection from delta I onto Li embeds into delta I, and that projects onto Li. Now the kernel, by our assumption, the first condition in the definition of the highest weight category, has a filtration whose subquotients are Lj, where j is strictly smaller than I. So by the inductive assumption, the projective dimension of this kernel is at most m minus 1 plus I minus 1 minus 1. And then, by the dimension shift, the projective dimension of Li can only increase by 1. That's because the projective dimension of delta I is fairly small. It's at most m minus 1, and we are talking about a much bigger number. So by the dimension shift, the projective dimension of Li is at most m minus 1 plus I minus 1. And that completes the proof. Now, before we go forward, let us define a certain Serre subcategory of a highest weight category. Assume that A mod with respect to our linear order is a highest weight category. Consider the Serre subcategory Q of A mod, which is generated by the simples L1, L2, and so on, Lm minus 1. We just forget the maximal simple Lm. Then, of course, the inclusion of the Serre subcategory into A mod is exact, and so it has a left adjoint, which we denote by capital Z. So the left adjoint of an exact inclusion is just the taking of the maximal quotient which belongs to our subcategory. So being left adjoint to an exact functor, Z sends projectives to projectives. And so, in order to describe projective objects in our category Q, we take the corresponding projective Pi, where now I is between 1 and m minus 1, in A mod, and apply our functor Z. The resulting module Pi upper Q will be the indecomposable projective cover of Li in category Q. So this works for I between 1 and m minus 1, because these are the simples which go to our Serre subcategory Q. And then, as usual, this category Q is equivalent to the category of finite dimensional modules over the opposite of the endomorphism algebra of the direct sum of all these indecomposable projectives Pi upper Q, where I is between 1 and m minus 1. So Q is also a module category over some finite dimensional algebra. And now, with this category in place, we can describe something which we can call the inductive nature of the definition of a highest weight category. First of all, of course, our fixed linear order on L1 and so on Lm induces a linear order on L1 and so on Lm minus 1. It just restricts to a linear order on simples in our smaller category Q. Proposition: the category Q, with respect to this restricted linear order, is a highest weight category. Proof: take I between 1 and m minus 1. So this is the indexing set of simples in Q. Then the standard module delta I from A mod remains standard in Q simply by construction. It's a maximal quotient of Pi, whose simple subquotients are indexed by I minus 1, and so on. And all these simple subquotients live in Q, so delta I remains standard in Q by construction. The fact that the kernel of the projection from delta I to Li has correct composition subquotients is directly inherited from A mod. They are indexed by strictly smaller indices than I, and all those indices remain in Q. Also, the indecomposable projective cover P upper Q is a quotient of Pi by the trace of the maximal projective Pm in Pi. Since Pi has a filtration with standard subquotients in A mod, because A mod is a highest weight category, that trace is a direct sum of copies of delta M. M is a maximal index in A mod, which is just the projective module Pm. And if we factor out this, we get a module which has a filtration with subquotients delta J, where J is between 1 and M minus 1. And this means exactly that Pi upper Q has a filtration with correct standard subquotients. And this completes the proof of our proposition. Now we can formulate and prove the following very important result about the connection between homological properties of A mod and this category Q. Theorem: if A mod is a highest weight category with respect to our linear order, then for any two objects M and N in Q, and for any non-negative integer k, we have an isomorphism between the case X group from M to N in Q and the case X group from M to N in A mod. So all extensions between objects in Q are the same in Q and in A mod. Proof: let P dot be a projective resolution of M in A mod. Since M is in Q, so capital M doesn't have L lower index small m as a subquotient, and since the trace of the projective Pm, that's a maximal projective, in any projective Pi is a direct sum of copies of Pm, the trace of Pm in our complex P dot is a contractible subcomplex. Okay? So at each homological position, this trace is a direct sum of copies of the projective, and for those projectives, the top part cannot belong to the homology. The only homology is M, and there is no Lm in that homology. So this follows that that's a contractible subcomplex. And also, this trace is in the kernel of any map from any position in our complex P to any homological shift of N, because now the module N is in Q. This should be N. Since N is in Q, Pm doesn't map to N, because N doesn't have Lm as a simple subquotient. Great. But then this means that this trace has no effect on the homology of the complex, which you get when you take the homomorphisms from our complex P dot to N. So if you compute this homology with the trace present in our complex, you get just the definition of X from M to N in A mod of any degree. And if you factor this trace out and compute the homology, you will get the projective resolution of M in Q, and so the resulting complex, the homology of the resulting complex, will give you the extension from M to N in Q. And since this trace is irrelevant for the computation, the two things coincide. And that's what proves our theorem. Recall that during the previous lecture, we also defined the notion of a costandard. Let I1, I2, and so on Im be the indecomposable injective A module. So the costandard module nabla I, where I is between 1 and m, for the pair A, our linear order on the set of simples, is defined as the cotrace kernel of the module I sub I into the injective modules I sub I plus 1 and so on, all the way up to I m. So let A op be the opposite algebra to A. Then left A op modules is exactly the same thing as a right A module. And we have the duality functor over our field. So taking the dual space with respect to our field, that's a contravariant equivalence between left A modules and right A modules, which means between left A modules and left A op module. And if we just compare the definitions, we see that this equivalence swaps standard and co-standard modules. So in particular, it maps co-standard A modules to standard A op modules. Our ultimate goal for today is to compare the property of A mod being a highest weight category and A op mod being a highest weight category. In order to do that, we first will discuss the homological orthogonality property between standard and co-standard modules. A corollary from our homological fullness theorem: if A mod is the highest weight category with respect to our linear order, then for all indices I and j and any positive integer k, we have that the dimension of the extension space over A of degree k from delta I to nabla j is equal to little delta ij times little delta k0. Here, little delta is the usual notation for the Kronecker sigma. Proof. Let us first note that if k is equal to 0, that's the case when we talk about Holmes. So if we want to compute the Holmes space from delta I to nabla I, this has dimension 1. Because delta I has simple top Li, it has this Li with multiplicity 1, and nabla I has simple socle Li. So if you want to map delta I to nabla I, the top Li of delta I should map somewhere, and it can only map to the socle of delta I, because if it would map higher up than the socle, then something else in delta I should map to the socle of nabla I, but Li appears in delta I only once in the top, a contradiction. After this observation, let's do induction on the maximum of I and j. So if I is equal to m, then we know that delta m, the corresponding delta I, is just the projective module Pm. And then the statement is clear. If we put the projective module Pm here, then all x vanish of higher degrees than 0. So delta m has a unique home to nabla m, and delta m, so Pm, doesn't have any homes to nabla j's for j is smaller than m by construction of nabla j. So in this case, the statement is clear. If j is equal to m, then nabla j is the injective module Im, and by the same arguments, the statement is again clear. If both I and j are strictly smaller than m, then we can use the homological fullness theorem and just forget Ln. We go to Q, to our Serre subcategory, which is generated by all simples except Ln. And so by induction on m, we get the claim. And the point of the use of the homological fullness theorem is that going from A mod to Q preserves all extensions. Great. Now we can formulate our main theorem for today. Theorem: if A mod with respect to our linear order is a highest weight category, then A op mod with respect to the same linear order is a highest weight category. So this means that A mod with respect to some order is highest weight, if and only if A op mod with respect to the same order is highest weight. Here is the reformulation of the statement. Reformulation: if A mod is a highest weight category with respect to our order, then for each index I, the cokernel of the inclusion of Li into nabla I has a filtration with subquotients Lj where j is smaller than I, And for each index I, the cokernel of the inclusion of nabla I into II has a filtration with subquotients nabla j, where j is strictly greater than I. This reformulation is obtained from the original formulation by applying the vector space duality. Let us prove this theorem. Due to the inductive nature of highest weight categories, to prove our first claim, it's enough to prove it for the index m. So it's enough to show that the module Lm appears in nabla m with multiplicity 1. If not, if this were wrong, there would be a homomorphism from Pm to Im is our nabla m, which doesn't send the top Lm of Pm to the socle of Im. But that's not possible because by the first condition of the highest weight category, Lm appears in Pm only in the top. So it appears with multiplicity 1. So this contradiction establishes this first property in the reformulation. So now we need to prove the second property. Let's prove the second claim. Again, we use the inductive nature of the highest weight categories, and we prove the second claim essentially only for the maximal weight. So we prove that for each injective II, if we take the quotient of II by the cotrace kernel of II in Im, this will be a direct sum of copies of Im. Assume that this is not the case. This would mean that we have the following first steps in the injective co-resolution of our cotrace kernel of II in Im. So it by definition embeds into II, and then the cokernel embeds into Im plus Im and so on several times. And then it doesn't stop there, and it embeds further. So we denote this new injective module at this position simply by I, and by construction, any summand of I should be of the form ij for some j strictly smaller than m. That's because all Lm simples inside II are covered in this direct summand. So everything what appears here has an index strictly smaller than m. But this means exactly that over A mod, the second x from any Lj appearing here into the cotrace kernel is non-zero, because in the minimal injective co-resolution, you have the corresponding ij here appear. So at this stage, we can use our homological fullness theorem and say that so Lj and cotrace kernel, they both belong to Q. So this second x non-zero implies that the second x in Q from Lj to this cotrace kernel is non-zero. Recall that Q is exactly embedded into A mod. So we have already used the left adjoint of this embedding. Now we are going to use the right adjoint, Z hat. So that's the right adjoint. It's described as taking the maximal submodule which belongs to Q. So being a right adjoint to an exact functor, this sends injectives to injectives. In particular, if we apply it to an injective cogenerator of some Ls, where S is smaller than M, we will get the corresponding indecomposable injective envelope in Q. And from the descriptions that it's taken the maximal submodule that belongs to Q, it follows that the application of this functor to Is gives you exactly the cotrace kernel of II in Im. In other words, this cotrace kernel is injective in Q. And on the previous slide, we established that the second x from Lj to this cotrace kernel in Q is non-zero. And that's a contradiction. This contradiction completes the proof. So let's now do an example. We consider the path algebra of the same quiver as in the previous example. So we have the vertices 1, 2, 3, and 4, and arrows from 1 to 3, from 3 to 2, and from 3 to 4. We already know that the category of modules over it is a highest weight category. We computed that projectives have filtrations by deltas and so on. So now let us check the same thing using injectives and nablas. The injective modules, we go against the arrows. 1 is a source, so the injective at 1 is just L1. To 2 we can go from 3, and to 3 we can go from 1. So the adjective at 2 has top 1, then middle part 3, and then socle 2. 3, if it have a socle 3, then we can go to 3 from 1. So I3 has top 1 and socle 3. And I4, to 4 we can go from 3 and to 3 from 1. So I4 has top 1, middle part 3, and the socle 4. Now let us compute diagrams of costandard module. The costandard module nabla 4 is equal to I4. We know that. The costandard module nabla 3 is the maximal submodule of I3, which has composition subquotients 1, 2, and 3. But I3 only has such subquotients, so nabla 3 is equal to I3. The costandard module nabla 2 is the maximal submodule of I2, which has composition subquotients 1 and 2. But that's just 2 because we have 3 in the middle, 3 is not allowed, so we just have 2. So nabla 2 is L2. And finally, nabla 1 is the submodule of I1, which only has 1. So that's I1. So these are our costandard modules. Now let us check our conditions. So nabla 4 has only composition subquotients 1, 2, 3, and 4, so 1, 3, and 4. And if you forget 4, we only have 1, 2, or 3. Correct. Nabla 3, we have 3 in the bottom, in the socle, and if you forget it, we have only 1. Good. And nabla 2 and nabla 1 are simple, so for them, everything is automatically satisfied. Now the filtrations of injectives. I4 is nabla 4, so everything is great. I3 is nabla 3, everything is great. I2 has nabla 2 in the socle, here in the bottom, and then if we factor it out, we get nabla 3. So that's okay. And I1 has nabla 1. So the consequence, the category of modules over the path algebra of the opposite quiver to our original quiver is a highest weight category. At the end of today's lecture, let us discuss the notion of a simple preserving duality. That's something which we will sometimes use in this course. Let A be a finite dimensional K algebra, and L1, L2, and so on Ln a full and irredundant list of representatives of isomorphism classes of simple A module. Definition: a contravariant involutive equivalence, denoted by star, of the category of A mod is called a simple preserving duality, provided that if we apply it to a simple module, we get an isomorphic module for any simple A module. Note that in the case when we know that A mod is a highest weight category with respect to some linear order on simples, and additionally it has a simple preserving duality, then the dual of the projective module Pi is the injective module Ii, and the dual to any standard module delta I is the costandard module nabla I. This all follows from the definitions because the duality is simple preserved. Remark: if A mod has a contravariant self-equivalence, then this self-equivalence maps projectives to injectives and hence induces an isomorphism between A and A op. Here we assume that A is a basic algebra. Conversely, any isomorphism between a basic algebra A and its opposite algebra induces, by composing with the vector space duality, a contravariant self-equivalences of A mod. So we know that if we are only interested in A mod, we may always assume that A is a basic algebra, and so contravariant self-equivalences of A mod, they come from isomorphisms between A and A op. Let us here discuss one such example. So consider the path algebra A of the following quiver. We have two vertices, 1 and 2, and two arrows, alpha from 1 to 2, and beta from 2 to 1. And we also have the relation that alpha after beta is equal to 0. So here, the algebra A is obviously isomorphic to the opposite algebra, where the involutive isomorphism psi preserves the trivial passes both at 1 and at 2 and swaps alpha and beta. Note that this is well defined because of the following computation. If we apply psi to our relation to alpha beta, then this is equal to psi of beta after psi of alpha. This is because psi is an isomorphism with the opposite algebra. We have to swap the product. And now psi of beta is alpha, psi of alpha is beta, so we get alpha beta, which is equal to 0. So our psi preserves the relations. It sends the relation to a relation. And so it induces a contravariant self-equivalence of the category A mod if, as discussed on the previous slide, we compose this isomorphism with the usual vector space duality. So this self-equivalence is involutive because our isomorphism squares to the identity. If we do psi twice, then we swap alpha and beta back, and we have the identity morphism on A. And this self-equivalence is simple preserving because psi applied to epsilon I is equal to epsilon I for I equal 1 and 2. So it preserves the trivial passes at each idempotent, and so it preserves the simple modules. Let us now check how this is coordinated with the highest weight structure on the category A mod. So the diagrams of projective and standard modules over this algebra are as follows. So P1 has 1 on top, and then we can use alpha to go to 2, so we have 2 in the middle, and then we can use beta to go to 1. Beta after alpha is not 0. It's alpha after beta, which must be 0. And so P1 has 1 on top, 1 in the circle, and 2 in the middle. P2 has 2 on top, and then we can go by beta to 1, and then we are stuck because alpha after beta is 0. So P2 has only 2 on top and 1 in the circle. Now about deltas. Delta 2 is P2, and delta 1 is a quotient of P1 by the trace of P2 in it. So we have to kill 2, 1 here, and we have just 1. And we see that P1 has a filtration with delta 1 on top and delta 2 here below it. And of course, delta 1 has 1, and delta 2 has 2 on top, and then in the radical, we only have 1. So this means that our A mod is a highest weight category. And now for injectives. So I1, we start from 1 in the circle. Then we can go by beta against beta and have 2 in the middle. And then we go against alpha and we have 1 on top. So actually I1 is isomorphic to P1, but it's now considered as an injective module, so we take a look at its circle. And I2, we can start with 2 in the circle, and we go against alpha to get 1, and then we cannot proceed further because alpha after beta must be 0. So I2 has circle 2 and top 1. So nabla 2 is I2, and nabla 1 is a maximal submodule of I1, where only ones are allowed. So it's L1. And so we see, first of all, that Pi is just a dual of II. So we take this P1 and we flip it, we turn it over, and we get I1. We take P2 and we flip it, and we get I2. And similarly, nabla 1 is a dual of delta 1, nabla 2 is a dual of delta 2. And also that I's have costandard filtration, I2 is costandard, and I1 has circle nabla 1, and then on top we have nabla 2. So this completes this example. We have now a module category which is highest weight and which has a simple preserving duality. Some problems and questions at the end. Problem question 1. Construct a counterexample to the homological fullness theorem in the case when A mod is not highest weight. Problem question 2. Check with all details that the K-duality maps costandard A modules to standard A-op modules. Problem question 3. Fill in all the details in the induction step of the homological orthogonality corollary. Problem question 4. Let psi be an automorphism of A. Show that twisting an action by psi is an autoequivalence of A mod, and that this autoequivalence is isomorphic to the identity functor if and only if psi is an inner automorphism. Problem question 5. Determine whether the module category of the path algebra of the following quiver with relations is a highest weight category. We now have 3 vertices 1, 2, and 3, an arrow alpha from 1 to 2, an arrow gamma from 2 to 3, an arrow delta from 3 to 2, and an arrow beta from 2 to 1. And we have the relations gamma after delta is 0, gamma after alpha is 0, beta after delta is 0, and alpha after beta is equal to delta after gamma. Thank you very much, and see you next time.